Standard transformer architectures carry a hidden cost. They rely on continuous floating point math, forcing models to approximate values at every layer. The prime power transformer eliminates this precision leak, mapping every single tensor operation directly onto a discrete geometric lattice. This framework implements a 13-step algebraic substitution, replacing the standard inference pipeline from embedding lookups to residual stream accumulation with exact ring operations. This diagram illustrates the bedrock of that substitution. We move from a continuous floating point space to the ring of integers, O sub k, belonging to the imaginary quadratic field of q root -163. Notice how the nodes isolate perfectly. We use -163 specifically because its class number is exactly 1. In number theory, this guarantees the structure is a principal ideal domain. Because it is a principal ideal domain, it strictly acts as a unique factorization domain. Every mathematical element inside this space factors uniquely into prime components without ambiguity. When every number breaks down into strict, indivisible prime factors, operations become perfectly lossless. Unique factorization provides a path to mathematical exactness, removing the cumulative error inherent in floating point quantization. We can see this exactness in the Frobenius endomorphism scaling equation. Shown here over a quantized attention matrix, the equation maps x to pi sub p to the k times x. Inside a unique factorization domain, the per-row scale factors lift uniquely to a Frobenius invariant unit. As the calculation proceeds, these scale factors cancel out completely. The math reduces without remainder. This exact Frobenius cancellation makes a heavily quantized matrix multiplication bit identical to a full precision 64-bit floating point reference. With scaling solved, the execution layer shifts to the negacyclic cyclotomic ring, denoted as R sub q. Negacyclic polynomial multiplication replaces the traditional attention dot product. By moving from an order n squared scalar grid to an order n log n pipeline, we reduce the total multiplication count for a 256-dimensional head by a factor of 16. To execute this polynomial arithmetic, the architecture uses the number-theoretic transform, or NTT, processing the signal through a sequence of modular butterflies. Shifting attention to polynomial rings over modular integers allows the architecture to track the theoretical speedup of the NTT, reducing the arithmetic intensity of the attention head. Once data is computed, it has to be stored and deduplicated. To find semantic overlap across the network, we first map high-dimensional vectors into strict combinatorial objects. This Vilenkin hierarchical transform, VHT2, applied to a 128-dimensional key vector, organizes coefficients by their prime factorization. A Mobius reorder then shifts the indices. Square-free indices move front, composite numbers cluster back. Those front-loaded square-free indices are mathematically indivisible by squares. They are the multidimensionally primitive data points, which we define as the anchors. The trailing composite indices provide higher-order corrections. These are defined as the residuals. This structured data packs tightly into a frozen 63-byte spinner block, which holds 1 global scale, 8 anchors, and 55 residuals. This code snippet shows the SP tensor entry structure. The block size field on line 168 enforces a 64-byte on-disk granularity. With a 63-byte payload, the 64th padding byte holds a hex A5 sentinel value to catch zero-fill corruption. By aligning mathematical data exactly with physical disk sizes, the system uses pure memory mapping. The file itself is the in-memory layout, removing data transformation overhead during loading. To deduplicate this exact data, the Knight Spiner tree encoder interprets the packed Spiner block as a strictly combinatorial object. The encoder converts the block into a rooted tree capped at 60 nodes. The root branches into depth 1 nodes labeled A, derived from anchors. Positive residuals get label B, negative residuals label C, cascading downward. The KSTE operates on a strict rule. The magnitude rank of the raw coefficient is converted directly into structural depth on the tree. This creates a mathematically rigid object where semantic subsumption, one concept containing another, correlates perfectly to whether one tree visually embeds within another. Representing raw attention vectors as trees allows the system to apply the combinatorial logic of Kruskal's tree theorem to cache management. Kruskal's tree theorem states that the set of finite-rooted trees with labels from a well-quasi-ordered set is itself well-quasi-ordered. The theorem implies that any infinite sequence of these finite-labeled trees will eventually produce a dominating tree. In the context of a cache, this means semantic novelty is not an open-ended resource, it is mathematically finite. The Friedman sieve realizes this theorem in hardware. An incoming tree hits the Tier 0 filter, executing a 64-bit integer subtraction check. Isolating node counts and maximum depth, it rejects non-dominating trees instantly. Surviving trees hit Tier 1, performing a 16-byte SIMD comparison of ancestor-descendant label pairs. Only the tiny fraction of trees that survive both hardware tiers undergo the expensive structural homeomorphic embedding check. Friedman's refinement of Kruskal's theorem proves that the length of any sequence of mutually incomparable trees in this 60-node space is finite. This provides an absolute mathematical ceiling for semantic novelty, effectively bounding the KV cache storage requirements even as the context window extends. With single-node memory bounded, the challenge scales up. How to handle distributed storage and aggregation across a federated network? The answer is algebraic resonance memory, or ARM. It functions as a holographic reduced representation built directly inside the negacyclic cyclotomic ring. The ARM binding operator relies on negacyclic convolution, packing keys and values into a single polynomial ring. Add 10 bindings or 10,000, the physical memory footprint never increases. Multiple bindings just accumulate via simple ring addition. This commutativity allows peers to integrate new data through simple gossip protocols without requiring network consensus. But it carries a strict trade-off. Recall fidelity degrades at the scale of 1 over the square root of k, meaning noise increases relative to the signal as more bindings are packed into the same ring. To mitigate this noise, the system uses 3-gap phase space equidistribution to generate deterministic keys that remain near orthogonal, maintaining retrieval accuracy at scale. By maintaining a fixed physical footprint as data volume grows, ARM breaks traditional linear memory scaling, enabling multi-mode associative memory to aggregate attention vectors with controlled, bounded capacity loss. Executing this advanced cyclotomic math on standard 64-bit hardware infrastructure requires dividing the heavy arithmetic across entirely parallel lanes. The solution is dual prime CRT sharding, which splits a 60-bit multiplication into 2 independent operations utilizing specific Proth primes. This uses 2 frozen constants, Q1 at 1,073,738,753 and Q2 at 1,073,732,609. Shard A holds residue modulo Q1, shard B holds modulo Q2. Held independently on separate nodes, neither shard contains usable information, securing the data across the federated cache. When a peer node retrieves both independent shards, standard Garner reconstruction perfectly recreates the original 60-bit mathematical object. From exact inference inside a unique factorization domain, to topological compression through Kruskal's theorem, to distributed holographic storage. A single prime-factored coordinate lattice provides the foundation for inference execution, caching, and network storage.